So why do we need to talk about any of this for chemistry? Well, we need to understand the concepts of exothermic and endothermic processes. So the energy of the universe is constant, but the universe is a little too big for us to think about the whole universe. And so what we tend to do is we think about a teeny tiny part of the universe. We focus on what we call in science the system. And the system can be anything that you want it to be. It could be your body, it could be the classroom, it could be a little test tube with some liquid in the bottom of it. The system is just the part of the universe that you choose to focus your attention on. The surroundings then are the rest of the universe. So the system is just the particular thing that we are looking at, and then the universe is the surroundings, everything else. So this idea of exothermic, endothermic process depends on what we define as the system. So let's think about a match. And so the match is going to be our system. We're going to look at the match and what's happening to the match. The rest of the universe is the surroundings. That would include the air around the match. It would include your fingers. It would include Timbuktu, Beetlejuice, anything outside of the match. The match has potential energy. It's stored in the form of chemical bonds. If you take that match and you strike it, what happens? It bursts into flame. And it gives off heat, doesn't it? And it gives off light. Heat and light are forms of energy. So on this graph, we're showing potential energy increasing as we go up. So initially, this match has relatively high potential energy. After we burn it, what's left over, the product, has less potential energy. This no longer has the potential to just burst into flames. It's all burned up, so it has less potential energy. All of these energy measurements are necessarily relative. So we're always looking at one thing compared to another. We can't really point a reference as something with zero energy. So we're always looking at changes. So the change in potential energy has been negative. What happened to that potential energy that it had initially? It gets released to the surroundings. So we have energy that's released to the surroundings as heat, and there's also some light generated, which is a form of energy. This is called an exothermic process. An exothermic, let's start down here. Exothermic process is one in which energy flows out of the system. We've got two terms here, exothermic and endothermic, and the difference is in this prefix. Exo is like exit, and the blue exit sign by the door. What does exit mean? It means to go out. An exothermic, thermic relates to energy, to heat. Exothermic means heat is exiting. It's exiting the system. Now, the total energy of the universe is still constant. So the energy being lost by the system is being gained by the surroundings, and in the universe overall, there's no change in energy. An endothermic process is the opposite. Endo is going in. Heat flowing into a system. It's absorbing energy from the surroundings. The surroundings lost energy, the system gained energy. But overall, the universe is still constant energy. So let's think about the freezing of water. When water freezes, what's going on? Is it gaining energy or losing energy? It's losing energy. It's a little bit hard to think about. Burning a match is easier. You burn the match and you could feel the heat coming off. Freezing water is also exothermic. Sometimes it's helpful to think about the opposite. What about melting ice? How do you melt ice? You heat it. You put energy into it. You can melt ice in your hand. The heat is coming from your hand. Your hand is warm, the ice is cold. There's a flow of energy from your hand to the ice. As the ice absorbs that energy, the particles move faster and it begins to melt. So the opposite process, taking water and freezing it into ice, you have to suck energy out. That's what your freezer and your refrigerator are doing at home. There's a motor and a compressor in there, and basically what that is a box with a device that sucks heat energy out of the inside. Where does that energy go? Can you cool your kitchen by leaving the freezer door open in the summer? No. Because the motor is giving off heat in the back. And it's because it's not 100% efficient, and nothing is, it's giving off more heat than what it's sucking out of the inside. Just kind of as an aside, a great place to dry tennis shoes is on the floor in front of your refrigerator. My kids do this periodically. They'll get their shoes just sopping wet. So you stick them in the washer on the spin cycle to spin out all the extra water. You don't want to dry tennis shoes in the dryer. The heat does nasty things to them. But then you take those now damp tennis shoes and you set them on their sides in front of the refrigerator. The refrigerator's pulling all this heat out of the inside and it's blowing it out underneath. And so you have this nice warm air coming out, not hot enough to damage your shoes. And you leave them overnight, they'll be dry in the morning. It's awesome. So that was, that was a tangent. So freezing of water. Freezing of water, the water is our system, and the surroundings is everything else. In order for the water to freeze, we have to pull energy out of it. So freezing of water is an exothermic process. Things that give off heat, like burning a match or even something like a glow stick where we see energy coming out in the form of light, those are easier to identify as exothermic. Freezing water is something that you have to do something to it to get that energy to come out. Freezing water being an exothermic process is why the farmers water their citrus trees when it's getting too cold, right? We had a bad freeze last fall. It's not good for oranges to freeze. So the farmers water. They water and water and water. How does that help? That water's not that warm. It's coming out of the ground. It's pretty cold. In order for the water to freeze, as it cools down and begins to freeze, it gives off heat. And it moderates the temperature. The temperature of the air near that water can't drop below freezing, which, we tend to think of it in Fahrenheit, 32 degrees Fahrenheit. The air around that water that's beginning to freeze can't drop below 32 until all the water is frozen. And the citrus trees is, about 26 degrees is the really dangerous point. And so just that little bit of heat from the water freezing will keep the whole orchard a little bit warmer and can protect the trees. And then you throw in some wind machines to help blow that air around, and you can fend off some freezes. So there's practical application of this. Here's another concept check. Classify each as exothermic or endothermic. And then the dreaded word, explain. Explain. So in each of these examples, the system is underlined because we have to know what is the system and what is the surroundings. So your hand gets cold when you touch ice. We're thinking about your hand. Is energy leaving your hand or coming into your hand when you touch ice? It's leaving. So then that would be an exothermic process, right? When you touch ice, your hand gets cold because energy is moving from your hand to the ice. That's why it's exothermic. And then B, we're switching it up, looking at the ice as the system, and everything else as the surroundings. So from the point of view of the ice, is it exothermic or endothermic? It's endothermic because there's energy from your hand going into the ice, and so that's endothermic. It's a little bit like a financial transaction. You have a question?
I've seen those packages that you break and it turns cold,
Mm-hmm.
or it turns warm to warm up.
Instant ice packs and instant hot packs.
Those are
Yeah, so an instant ice pack, when there's usually some sort of a little pouch inside, there's two chemicals in there. When you break the pouch and mix the chemicals, a reaction occurs for the cold pack that absorbs energy from the surroundings. For the hot pack, it's going to be an exothermic reaction. The two things mixed together, the potential energy stored in the bonds, will come out as heat. So in a financial transaction, you've got someone giving money and the other person accepting the money. And whether that's an inflow or an outflow depends on who you are, right? It's an inflow for one person and an outflow for the other. So we can think of energy, these energy transfers as being a little bit like money. It depends, whether it's positive or negative, depends on who you are. How about water boiling in a kettle being heated on the stove? The water, from the standpoint of the water, what's happening? Endothermic, right? We're putting energy into the water to cause it to boil. What about water vapor condensing on a cold pipe? So we've got water in the air in the gas state, and when it encounters a cold object, a pipe, or maybe a glass that has ice in it, you notice glasses of ice water will sweat, right? Water develops on the outside. Does that mean your glass is leaking? No. The glass is cold because of what's inside of it, and there is water vapor in the air. When the water vapor contacts that cold surface, there's a temperature difference and there's an energy flow. Heat leaves the water in the gas state and goes into the glass. That's an exothermic process. So water vapor condensing is an exothermic process. Water boiling is going from the liquid state to the gas state. That's an endothermic process. Water condensing is the opposite, going from a gas to a liquid. And so one's endo and one's exo. Ice cream melting. The ice cream. Is the ice cream endothermic? Because energy is going into the ice cream to cause it to melt. So you should be able to identify whether a process is exothermic or endothermic. Some of the questions in the homework may be a little, could be a little confusing on the exam. I do my best to choose examples that should be obvious. So, things like ice in your hand. I think we've all experienced that, and so we should all be able to think about that. I know you guys are all anxious to leave. I've got 5 more minutes. For each of the following, define a system and its surroundings and give the direction of energy transfer. So now they're not telling us what the system is. They're saying, okay, you pick the system and then tell us what direction the energy is moving in. So methane is burning in a Bunsen burner in a laboratory. Okay, we've all experienced that. We've done this in lab. So we need to choose the system. Pardon me? The methane. Okay, the methane is the system. We'll choose that. So then is this exothermic? Is the direct energy leaving? Yeah, so this is exothermic then when we define methane as the system. What about when the lab is really, really cold and we light the Bunsen burners to warm the place up and we sit there and we warm our hands? If we define the system as our hands, then is it exothermic or endothermic? It's endothermic because our hands are absorbing energy. So it very much depends on how you define your system. Water drops sitting on your skin after swimming, evaporating. So the two obvious choices for system would be the water drops and your skin. Which one do we want to do? The water drops. So the water drops are on your skin. How is the energy flowing? Is it flowing from the water to your skin or from your skin to the water? It's flowing from your skin to the water. So from the standpoint of the water, that's endothermic, isn't it? From the point of view of your skin, though, that's exothermic. When we sweat in the summer, or when you get out of the pool and you're dripping wet, do you feel warmer or cooler? You feel cooler, right? The wetness on your skin makes your skin feel cooler because there's energy being transferred from your skin to the water. And that's why we sweat, is sweating helps cool you off. Here where we have a nice dry climate, it works really well. I grew up in Iowa where it's very humid in the summer and sweating does almost no good. When it's 95 degrees and 95% humidity, you can sweat all day long and almost nothing will evaporate. It's really miserable. So let's say we have hydrogen gas and oxygen gas and they're reacting violently to form water. Which do you think is lower in energy? A mixture of hydrogen and oxygen gases or the water? Which is lower in energy? The water. Then we're supposed to explain. The hydrogen and the oxygen have a potential to react violently. They have stored potential energy in their bonds. And when we set off that reaction, usually just a small spark will cause that to go. They react violently. So the oxygen and the hydrogen have higher potential energy, and the product has lower potential energy, the water. There we go, end of chapter.